Hello everyone. So in this chapter 1.2, we're going to be covering the topic of pre-calculus review once again, but this is the second part of that review. The first thing we're going to talk about is rational expressions. So what exactly is a rational expression? Rational expression, basically any quotients of what we call polynomials, okay, like we studied in the last chapter. Whenever you have one divided by the other, we're going to call it a rational expression, okay? So for example, the first one over here that we have, that I'm just now indicating, that one is a polynomial function, both on the denominator and on the numerator, so which will make this a rational expression. If you notice, the second one is also one and the third one as well. Okay, so what is important here? The important part here is that it is a rational expression as long as the denominator over there, the one at the bottom, is a polynomial function. Okay, so since rational expressions are quotients in which the variables represent real numbers, the properties of all real numbers also apply to rational expressions as well. And operations with rational fractions are performed in the same manner as operations with arithmetic fractions. What does that mean? Basically means that whatever operation you do with normal numbers involving ratios with normal numbers, the same properties apply to this type of function. So multiplication, division, subtraction, sum, all those things have the same rules. In other words, for example, okay, you can only add two different rational expressions as long as the denominator is the same. So here's another example. All right, so by using the properties of real numbers, okay, we can write, for example, that if I have AC divided by BC, I can rewrite this as A divided by B, okay, and C multiplied by C divided by C. And since C divided by C is 1, it cancels each other. It only becomes A divided by B. In other words, since A, B, and C are any real numbers, so B and C, as long as they're not 0, it's fine. So with the same sense, the sense that we can cancel, the operation we just did here was cancel. If you notice that I cancel the C with the C at the bottom, okay, if we know this, similarly we can use the same properties for real numbers, and we can rewrite, for example, this expression we have over here. All right, this expression over here where we have x plus 2 multiplied by x minus 3 divided by x minus 2 multiplied by x minus 3. I can actually cancel the x minus 3's, okay, I can cancel them, and I will get only x plus 2 and x minus 2. And remember, this is only possible, obviously, as long as x is different from 2 or 3, because otherwise on our original function, on our original rational expression, we would have a situation where we divide by 0. Okay, so this thing that we just did of canceling or cutting out two elements that are multiplying at the denominator and at the numerator, this is called canceling. Okay, canceling of common factors. So any algebraic fraction can be simplified, or in other words, in the lowest terms, when the numerator and the denominator have absolutely no common factors other than 1 and minus 1, and the fraction contains no negative exponents. In other words, we know that a formula is simplified, we know that a fraction is simplified when there is nothing for me to cancel out in the numerator and the denominator. So here's a couple of examples I want to go through. The first one, example A, we have x squared plus 2x minus 3 divided by x squared plus 4x plus 3. Now what happens here? Okay, what happens is, first of all, if you notice, from here to here, all right, so from the first part to the second part, just letting you know, I use the quadratic formula that I teach you on the first chapter. And on the bottom, I used again the quadratic formula in order to be able to find my zeros, to find my factors of those two polynomial functions. So I can rewrite the top one as x plus 3, x minus 1, and the bottom one I can rewrite as x plus 3 and x plus 1. Now what I notice here is that I can cancel two factors, right? I can cancel the x plus 3, right, which would result in x minus 1 divided by x plus 1. Can I cut anything else? Can I find anything else? No. In this case, what we can say that it is simplified. This formula is simplified. On case B, on the other hand, okay, I have a little bit more work to do. Now what I see is that on the denominator, all right, I have x square plus 1, and this is power 4. At the top I have a variety of things, okay, but what I see is that I have two things in common between these two terms. Okay, the two things in common I have is I have here a x plus 1, x squared plus 1, sorry, and I have also another one here, a x squared plus 1. So that means both terms have something similar, and what I did was to put that x squared plus 1, I put it out here, and then I open parentheses, and I basically am factoring out that x squared plus 1. So what is remaining from the x squared plus 1 initially that we had actually I'm gonna now just change colors here. This one over here that I just drew the arrow in purple, okay, I had it squared. I only need one out here now, all right, so the other one is right here, the other purple arrow, okay, and then I have also the negative 2 as well, that is indicated by the blue arrow, so the negative 2 comes over there. Then I have plus, okay, and I'm gonna now use the green color, all right, the green color, and I have 2x over there, that stays the same, I did not touch it. I have now with the orange these 2 over here, and the 2 comes down here. Then I have the x squared plus 1, but because I factored it out, I don't have to rewrite it. And finally, the last one that I have now in a black arrow, all right, is right there, my 2x. So basically what I did was to factor out that x squared plus 1. What's next step? Next step now, obviously, what I did was I simplified everything that was inside that big parenthesis, and I just joined, I expanded, all right, the similar terms, and now I carried out all the multiplications inside there. Then what I did was to combine the likely terms. For example, what I see here is that these two, 8x squared and negative 2x squared, can be joined together, and that's why now I just have a 6x squared. Next step now is to indeed cancel out the common factor. Now if you notice, I have here, I'm doing with blue now, x squared plus 1, and there's no power on it, so it's can be considered power 1. But at the bottom, at the denominator, sorry, I have a 4, so that means that I'm gonna go to this 4 and decrease 1, okay, because I'm canceling this one with this 4, and that's why over here I only have a 3, a power 3, and that is the most simplified version of this factor. As you can see, it is a little bit of work, but as long as you keep yourself organized, it's not a big deal. Finally, I could also, for example, if you wish, you could also factor 2 out, okay, because I have a 6 there and I have a 6x squared minus 2. I could factor the 2 out to simplify, but to be honest, this part is not absolutely necessary. So regarding this, I suggest you to write down the following formulas that you see on this table, okay. The operations of multiplication and division are performed with algebraic expressions in the same manner as with any other number. In other words, if you have, for example, this first rule, the rule of multiplication indicates that if you have a certain expression p divided by q, and if you have another expression r divided by s, those two multiplying, you can just rewrite the whole thing as pr divided by qs. And as long as q and s are different from 0, it's fine. So for example, over here on the example, what we need here is I have a 2x divided by y, I have a x plus 1 divided by y minus 1, so all I have to do is multiply one by the other, and I ended up with 2x multiplied by x plus 1 divided by y multiplied by y minus 1, which will end up in 2x squared plus 2x divided by y squared minus y, like you see in this expression over here. All right, now changing to purple my indications. All right, so we're gonna do the division formula. The division formula says if I have the expression p divided by q divided by r divided by s, I just need to switch the order, okay, I just need to invert one of the fractions and I can transform it into a multiplication. In this case, I decided to invert the rs, so the s comes to the top and the r comes to the bottom, and so I end up with p divided by q multiplied by s divided by r, which stands for ps divided by qr. So for example, here we have another example again in purple. All right, and I have x squared plus 3 divided by y squared plus 1 divided by x. So what I did is to switch again the order of the second one, so I still have my x squared plus 3 divided by y, and now I have it multiplied by x divided by y squared plus 1, which this will result in, like you see over here on purple, it will result in x power 3 plus 3x divided by y power 3 plus y. And these are the rules of multiplication and division. The next two rules, okay, is the rules of addition and subtraction, all right? And it works pretty much in the same manner, on the sense, for example, I can only do one or the other as long as the base and, as long as the denominator is the same, as long as the bottom part is the same. So in this first one, I have a r and a r at the bottom. So that means I can indeed add the p and q. So I have here an example as well. So, oops, my apologies. Let me eliminate that one. There you go. So I have here an example, 2x divided by x plus 2 plus 6x divided by x plus 2. Now, because the bases are the same, because the denominators are the same, all I need to do is I keep the base, x squared plus 2, and the top part I add 2x plus 6x, which will result in 8x divided by x plus 2, which is the solution over there. Now, regarding the subtraction, what we have is p divided by r minus q divided by r. I can do this operation as long as the denominator is the same, which is the same, and I end up with p minus q divided by r. Again, the example we have over here is I have a 3y divided by y minus x minus a y divided by y minus x. This will result in 3y divided by y divided by the common denominator, which is y minus x, and I end up with 2y divided by y minus x, as is indicated over there. So note though that you cannot do this situation over here. If you have, for example, x divided by 2 plus y, you cannot rewrite this. This is absolutely wrong to write x divided by 2 plus x divided by y. Okay, so to add and subtract fractions that have different denominators, first you need to find a common denominator. So preferably one that is the least common denominator, the number that you have to multiply that is the least number in common. Then you need to carry out indicated operations followed by procedure described on the table that I just showed you to you. So let's talk about this part, about finding a common denominator, finding the lowest common denominator of two or more rational expressions, okay? Well, step one is you need to find the prime factors of each denominator. In other words, you need to find the numbers that indeed, when multiplied by each other, multiplied by the denominator you have, it will allow you to find something in common with the other one. And then you need to form the product of the different prime factors that occur in that denominator. So each prime factor is this product should be raised to the highest power of that factor appearing in the denominators in order for you to actually obtain denominators that are the same. So, for example, okay, here I have two examples. Let's start with the first one. On the first one, I have 2x divided by x squared plus 1, and then I have plus 3x squared divided by x cubed plus 2. All right. So on this one, what do we see? We see that we cannot add them immediately. We see that there is indeed a problem because they are not the same. So what can we do? Well, when I look at that, I see one thing. In this case, all right, the easiest solution, there's nothing that I can multiply one of them that would allow me to obtain the other. There is no number that I can multiply x squared plus 1 that allowed me to get x cubed plus 2. So the solution for this is very simple. You multiply one by the other. You have to, the least common denominator is to multiply one by the other. So in other words, the part that you have, this x cubed plus 2, all right, this x cubed plus 2, for example, you will use it to multiply it by the 2x up there. And this x squared plus 1, you will use it and multiply it for the part over there. So what would you get? You would get 2x and x cubed plus 2, then plus the 3x squared and x squared plus 1. So notice that indeed in purple I have the denominator of the first one and I multiplied it by the numerator of the second one as well. I multiplied by everything on the second one. And on the second term I have x cubed plus 2 and I multiplied it there it is again. I multiplied by the denominator of the first one, the numerator of the first one, my apologies. This has allowed me indeed to obtain something that I can now add one to the other because they have a common denominator. So what we have now is expanding all that. I obtain 24x power 4 plus 4x plus 18x power 4 plus 18x squared. And this all divided by x squared plus 1 and x cubed plus 2. So in other words, I carried out the multiplications. On the next step, I combine the like terms, the terms that are similar, and I obtain 20x power 4 plus 18x power 2 plus 4x, all this divided by x squared plus 1 and multiplied as well by x power 3 plus 2. Finally, I can actually factor out the 2x out there, and that's the final solution for this exercise. The next one is 1 divided by x plus h minus 1 over x. Now in this situation, once again, I have to multiply one by the other, okay? And in this case, what would happen is obviously the first term, all right, this first term over here, you have to multiply everything by x, all right, because it's over there. And on the second term, the one in yellow, right, the one in green, sorry, you have to multiply all by x plus h. So what I obtain is x minus x plus h. On the top, why? Because 1 multiplied by this x over there would become just this x, okay, the one in green. And, all right, 1 multiplied by x plus h over there, which becomes this x plus h, all right? So I have now x minus x plus h divided by x multiplied by x plus h, all right? Then I remove the parentheses, okay? I switch the signs inside all the parentheses in the previous term, and I have x minus h. I simplify that to just minus h divided by x multiplied by x plus h, and that's my final solution. There's nothing else I can do because this is the simplest form of the fraction. Okay, let's now talk about other algebraic functions. So the techniques used to simplify rational expressions may also be used to simplify algebraic fractions, in which the numerator and the denominator are not polynomials. For example, what do I mean with this? Okay, let's check the next example, and I think it will make things much more. So in this example over here, what we see is that we have two expressions, one in the denominator, another one in the numerator. And for each one of them, okay, we're gonna have to find as well the least common denominator. So for example, on the first one, okay, in the numerator, the least common denominator would have to be x plus 1, because obviously there's just a 1 there, so I found it there. And the least common denominator for the denominator would be an x, because as well on the first one there's no fraction on it. So by using this, I multiplied, so seeing that, for example, analyzing that 1 is the same as having 1 over 1, okay, I multiplied the denominator and I multiplied the numerator by x plus 1, and that's why I obtain x, and that's why there I obtain x plus 1 divided by x plus 1. In the denominator, okay, I have the same thing. I had an x, okay, so I multiplied both x by x and I divide it once again by x minus 4 over x, and that's why here I have x squared minus 4 over x, okay. The next step is to actually use the multiplication rules, and now I have x plus 2 multiplied by x divided by x plus 1 multiplied by x squared minus 4, okay. And so I have x plus 2 divided by x plus 1 multiplied by x divided by x squared minus 4. And this will simplify to x plus 2 divided by x plus 1 multiplied by x plus 2, x minus 1. And now if you see, actually, I can actually cut this one over there. By the way, why did I simplify x squared minus 4 to x plus 2 and x minus 2? Because remember, whenever you have a number square, so a square, sorry for my handwriting with the mouse, I know it's bad, and a b squared, so if you have a squared minus a b squared, this is the same, or this is equal as having, okay, a minus b, and this multiplied by a plus b, and close parentheses. Okay, and that's what I have there. Once I have that, I can then cancel the x plus 2 in the numerator and in the denominator. So now I get x divided by x plus 1 and x minus 2, and there's nothing else to simplify. On the second example, I have x power minus 1 plus y power minus 1 divided by x power minus 2 minus y power minus 2. I can rewrite the x power. Whenever you have a number power minus 1, you can divide it as 1 divided by whatever the minus 1 was on the power of. So that's why I have 1 over x. Same thing for the y. I have plus 1 over y divided by 1 divided by x squared minus y divided by y squared. Once again, I have to find the least common denominator, and for that, I just multiply one by the other. All right, I just have to multiply the bases, and that's why on the first one, this 1 over x, I multiply it by y, and I would get the y over there. On the second one, this one over there, 1 over y, I multiply it by x, that's why I have a x over there. On the bottom one, I have to multiply the green one by y squared, and that's why I have y squared over there. And finally, I had to multiply in orange this one by x squared, and I get minus this x squared as well. All right. So by doing that, then I apply the multiplication law, and I have y plus x divided by xy multiplied by x squared, y squared divided by y minus x squared. Once again, I can simplify the y squared to x minus x squared, and I get y plus x, y minus x. And once again, I can factor this one out, cancel it, and I would get a solution of xy divided by y minus x. All right. And now we're going to talk about rationalizing algebraic fractions. So with rationalizing algebraic fractions, this part can be sometimes a little bit tricky. Like I explained to you, this comes from the rule that I just showed you, that whenever you have a number square minus another number square, you can actually rewrite that as a minus b multiplied by a plus b. So here in this situation we have when the denominator of an algebraic fraction contains sums or differences involving radicals, in other words square roots, we may rationalize the denominator. In other words, we can eliminate the square root by and transform that fraction into the equivalent one with a denominator that does not contain radicals. And in doing so, we can use this fact. For example, if you have, let's imagine you have in the denominator square root of a plus square root of b. If you multiply it by square root of a and square root of b, okay, you would actually obtain a minus b, and you can use this to eliminate rational ratios or square roots in the denominator. So every time I ask you to rationalize a fraction, what I'm asking you to do is to eliminate the square root of a denominator in a fraction. So for example, if I want to rationalize this one over here, I have 1 plus square root of x in the denominator, and I want to eliminate that square root. Like I told you before, all I have to do, all right, I could just multiply it by 1 minus square root of x. But obviously I cannot just multiply the denominator, I have to also multiply the numerator, and that's why the numerator, and that's why we have there. And basically I'm just multiplying by 1, because 1 minus x square root of x divided by 1 minus square root of x would be equal to 1. Now by doing this, it allows me to transform, and now I have 1 minus the square root of x squared at the denominator, and that comes from the previous rule. But square root of x squared is equivalent to just having x, and that's why now I have 1 minus square root of x divided by 1 minus x, and with this I have rationalized the expression. In other words, I have rationalized the denominator and I eliminated the square root from the denominator. I can also ask you sometimes to rationalize the numerator, and in that case you have to eliminate square roots from the numerator. Now we're going to go into inequality. So inequalities are basically expressions that indicate greatness or inferiority to other numbers or to relationships between variables. Before we dig into some examples, here are some properties we need to know. Okay, property 1 tells that if I have a number that is smaller than b, if a is smaller than b and b is smaller than c, then automatically a has to be smaller than c. In other words, for example, if 2 is smaller than 3 and 3 is smaller than 8, I can conclude that 2 is smaller than 8. Now in purple for property 2, it says that if I have a number a divided is smaller than b, then I can assume and I can conclude that a plus a certain number c still is smaller than b plus a certain number c. In other words, as long as you add the same number to both sides of the inequality, the rule stays equivalent. The other rule that says is if I have a number smaller than b, and I have a number c that is greater than 0, in other words, it's positive, then a multiplied by c will be still smaller than b multiplied by c. In other words, as long as I multiply a positive number by both sides of the inequality, the condition stays the same. And finally, the last rule is if I have a number smaller than b, a smaller than b, and if I have a number c that is negative, then a multiplied by c will now become greater than b multiplied by c. In other words, if you multiply both sides by a negative number, then you have to switch the sign from greater to smaller or from smaller to greater. So similar properties will hold for each inequality sign. So that means, for example, you can have the smaller than, okay, smaller than between a and b and between b and c, and if you replace it by greater or equal to or greater or smaller or equal to, in other words, it always stays the same. Although property 4 says that an inequality sign is reversed if the inequality is multiplied by a negative number. Don't forget that. So on this second paragraph here, it reads that a real number is a solution of an inequality involving a variable if a true statement is obtained when the variable is replaced by that number. And the set of all real numbers satisfying the inequality is called the solution set. In other words, inequalities will always have more than one solution, and we often use interval notation to describe this solution set. So for example, if I want to solve the equation x squared plus 2x minus 8 is smaller, okay, than 0, then observe though that I can rewrite x squared plus 2x minus 8 to x plus 4x minus 2. How? By using the quadratic formula from our previous chapter. I kid you not, but it's probably the formula we use the most in the upcoming chapter, so you really have to practice there. So given the inequality is equivalent to the inequality over here, okay, because I just rewrote it, all right? So given that, I rewrote that x plus 4x minus 2 has to still be smaller than 0. Now, and since the product of these two real numbers is negative if and only if the two numbers have opposite signs. What does that mean? If I'm multiplying two things and the multiplication gives me a negative number, there's only one solution. One of them has to be negative, the other one has to be positive. So we solve the inequality, okay? We are solving that by studying the sign of the two factors. I need to study the sign of x plus 4 and I need to study the sign of x minus 2. So for x plus 4, okay, for x plus 4 to be greater than 0, then x has to be greater than minus 4. And for x plus 4 to be smaller than 0, then x has to be smaller than minus 4. And what we see over here, okay, in red is that x plus 4, if it's minus 4, will be 0. To the left is negative, to the right is positive. Okay, now with purple, what we see, I'm switching to purple, for x minus 2 to be greater than 0, then x has to be greater than 2. And for x minus 2 to be smaller than 0, then x has to be smaller than 2. And obviously for the value of 2, it would be 0. So what I have there on with the purple indication is that there it is, at 2, my equation is 0. To the right is positive, to the left is negative. Okay, so now I need to look for where are the signs opposite. So over here, they're both positive. That means the multiplication of them both would be positive. Over here, they would be also, both of them are negative, but negative with negative would result in a positive number, and therefore cannot be the solution. So the solution will have to be, as you can see, between minus 4, not included, and 2, indicated by the red box. So from what we can see, like I just said, we see that the two factors x plus 4 and x minus 4 have opposite signs when and only when x is between minus 4 and 2. And therefore, the solution set would be the interval minus 4 and 2. But attention, minus 4 and 2 are not included in this. All right, now the concept of absolute value. So absolute value is basically a number, okay? It's a number that will always be positive. But let me give you the definition. The absolute value of a certain number a will be denoted by this denotation over here. So like two straight lines in between the number. And is defined by the following. So if a is positive, it stays positive. If a is negative, it becomes positive. And that's simple. In other words, absolute value always has to become positive. So since minus a is a positive number, when a is negative, it follows that the absolute value of a number, like I said, always has to be non-negative. So for example, absolute value of 5 will be 5. Absolute value of minus 5, I have to switch it to minus 5, and therefore will be 5 as well. So geometrically, absolute value of a is the distance between the origin and the point of the number line that represents the number a. In other words, that's why it's always, because absolute value does not represent value, but represents a distance, and distances are always positive. So here's a couple of properties regarding absolute value. First of all, the property 5 over here in red states that the absolute value of a negative number is the same as having the absolute value of the positive number. Okay, so in other words, I can just rewrite, if I have absolute value of minus 3, I can just rewrite it as absolute value of 3. In orange, okay, I have that the multiplication, if I have two numbers inside the absolute value multiplying, I can have the multiplication of their separate absolute values. Or in other words as well, if I have two absolute values multiplying, I can join them in the same one. Property 7, which I'm going to use purple, all right, states that the absolute value of a ratio is the same as the absolute value of each number divided by the other. And finally, property 8, which is the most important, okay, or the ones that is the most tricky, is that if I have absolute value of a plus b, okay, absolute value of a plus b, this will be smaller or equal to the absolute value of a plus the absolute value of b. In other words, you cannot separate you cannot just simply separate and say they are the same. Actually, if you have two numbers adding inside an absolute value, then when you separate them, their sum will be smaller. And this property has a special name. We call it the triangle inequality. So let's imagine I want to solve the inequalities. So absolute value of x smaller or equal to 5 and absolute value of x equal or greater than 5. So for the first, we need to consider that the inequality x smaller or equal to 5. If x is greater than 0 or positive, then I would have that the absolute value of x is equal to x. And so we can say that the absolute value of x to be smaller than 5 implies that x has to be smaller or equal to 5 in this case. On the other hand, if x is negative, then we're going to have that absolute value of x will be equal to negative x. And so my absolute value of x to be equal or smaller than 5 would imply that my minus x would have to be smaller or equal than 5. Or in other words, my x has to be greater or equal to minus 5. So what we see the solution here? What is the solution then for absolute value of 5 to be smaller or equal to 5? It means that the value of x would have to be between 5 and minus 5. To obtain an alternative solution, we can also see that the absolute value of x is the distance from point x to 0. So we can rewrite absolute value of x, and we can rewrite it as, for example, this. Minus 5 will be smaller or equal than x, which will be smaller or equal than 5. And I can just rewrite it like that. So next, I have the inequality when is absolute value of x smaller or equal than 5. This states that the distance from x to 0 has to be greater or equal to 5. And by observation from the previous results, we see one thing. We see that our solution would be like this. So any number greater than 5 would be a solution. So in other words, my solution set is 5 to infinity in this right circle over here, and my other solution would be negative 5 to negative infinity, which is over here. Alright, with this we reached the end of the video. I hope it helped, and let me know if there is any specific topics that you would like me to cover. I'll see you in the next video.